Right, I'd like to look today at precipitation, and I wanted to look at a couple of different ways to determine how a raindrop is formed. And so it may be something that you would imagine happens in, say, our latitude, when a small little tiny drop starts to gather with other small drops, become a bigger and bigger drop, and then it finally falls out as rain. Well, that's not how it happens in the higher latitudes.
Oh.
But rather, it is essentially frozen ice crystals that melt and turn into raindrops. It's only down in the tropics that we get smaller raindrops coalescing into larger ones and then producing what we call a tropical rainstorm. And so let's take a look then at how precipitation works at higher latitudes, like where we are. Here's a cloud. Say it's an unstable cloud. We could call this, with vertical instability, cumulonimbus. As it rises rapidly, typically there are three different sections to the cloud. In the top layer, this is all ice crystals. And these ice crystals tend to form when the temperature is less than -40 degrees Fahrenheit. And so most of you are probably thinking, well, why don't ice crystals form at 32 degrees? Because that should be the freezing point of water. 32 degrees Fahrenheit is the same thing as 0 degrees centigrade. And so we've learned that's the freezing point of water. And so why do we only see pure ice crystals at a temperature that is less than -40? Well, the reason for that is that these little water droplets are so small. They have a very small cross-sectional area. And so essentially, they can't find each other to coalesce into a solid crystalline kind of a structure. They miss each other. Until we get to a low enough temperature. And at that very, very low temperature, they slow down enough so that it is possible for them to coalesce into ice less than -40. But for temperatures that are less than 32 degrees Fahrenheit and greater than -40 degrees Fahrenheit, what we have is what we call a supercooled liquid. Meaning that if the conditions were right, we could form an ice crystal. But what we need is essentially a pre-existing ice crystal. And so essentially what we have then is a seeding of this region from -40 to 32 degrees with ice crystals. And so the ice crystals settle in or are seeded. They fall from the higher part of the cloud. And so now we have an ice crystal here, and these water droplets are going to collect on the ice crystal, and that causes the ice crystal to grow. So that as this happens then, in this middle layer, the ice crystals grow. And so we get a number of different very exotic and beautiful shapes for these ice crystals, which we can see here in this process of formation. We get a bunch of these little supercooled water droplets eventually collecting into these little crystals, but then that starts to become much more symmetric and a beautiful shape to these ice crystals. And so here are falling ice particles, and here is the water collecting to produce our ice crystals. And so in this middle region of the cloud then we have a mix between the ice crystals and the supercooled water. And so then these ice crystals form and they start getting a little bigger in this region. But then the temperature becomes greater than 32 in this lower region of the cloud. And so in this region then the ice crystals melt. And then we get rain. And so almost always the rain that you feel, say in this part of California or the middle of the United States, and anywhere from here on up, is the result of melted ice crystals and not due to a coalescence of smaller water droplets into larger ones. Now, in a cloud like this, typically there is an uptake, a place where air comes in. So we have an updraft here. And then the air cools, and in this region where we have the ice crystals seeding the supercooled water and then finally melting, we have the downdraft. And so what can happen then, and let me just redraw this to illustrate the kind of flow that we're talking about. Typically, this cloud is going to tend to be flat at the bottom. Because the temperature is dropping as a function of elevation. So we have lower temperature until finally we reach this temperature that's low enough to be at the saturation vapor pressure. And we talked about before with humidity. So this is happening, then the temperature is constant all the way along, and so the saturation vapor pressure then is going to be a consistent level line. And so that's why we oftentimes see the bottom of these clouds as being flat, because at all of these points we essentially have the same temperature, and because the air has the same amount of liquid in it, in the vapor state, it reaches the dew point and starts to collect and create a cloud at that saturation vapor pressure point. And so here then we can have updrafts, and then we can have downdrafts like this. And so typically the updrafts might happen here symmetrically, and then the downdrafts would happen, say, out near the periphery of the cloud. And so if you start getting these intense winds that are associated with these downdrafts, this is driving these ice crystals through the supercooled water and then forcing that water out of the cloud. And so we get a very strong storm surge that can develop if the winds are large enough in this outtake. So this is the intake of the cloud, and this is the outtake, or outflow of the air, which then can be associated, if the conditions are just right, with very heavy precipitation. And so that's the kind of precipitation then that we see at higher latitudes. But what about in the tropics? In the tropics, the cloud never gets cold enough to produce ice crystals. And so in that kind of a situation, you can get enough saturation so that smaller droplets turn into larger droplets. And so let's look here at some typical sizes for these water droplets when they're just getting started versus what happens as they start getting bigger. So here we would consider this point to be a condensation nucleus. Okay, so this would be maybe a particle of dust or something that could cause the water to start to collect on it. And so we're looking here typically at a size of about 0.2 micrometers. A 0.2 micrometers is on the order of maybe 1/10 the thickness of a human hair. Okay? And then we get to a little larger size. This would be a typical cloud droplet, and so that would be something like 20 micrometers. And then if we want to go to the typical raindrop size, look at how much bigger a typical raindrop is than the very smallest cloud droplet that we might see. Something like 2,000 micrometers. Now, 1,000 micrometers is the same thing as 1 millimeter. So this would be the same thing as 2 millimeters. And remember that 10 millimeters equals 1 centimeter, which is something like this size, 1 centimeter, a little less than that. 2.54 centimeters in an inch. And so the millimeter is a smaller gradation. And so 1,000 micrometers, or this is a millionth of a meter, is equal to 1 millimeter. So we have this as being the typical size of a raindrop. And so the question then is, how do we get from here to there? Well, we do so by means of accumulation or condensation of water on the droplet. Okay, and so what we tend to see here, though, is that as water tends to try to accumulate to the cloud droplet, the farther out we get, the more spread out the water droplets are. Okay, and so this has to do with the fact that the area of the drop is also related to the area that can evaporate off water. And so with a bigger drop like this, the area to volume ratio is a measure of how easily it is for the drop to evaporate. If we have a high area to volume ratio, then what that means is the drop will evaporate easily. And so, which one of these do you suppose has a higher area to volume ratio? The smaller cloud droplet or the larger raindrop? Well, we might say the larger raindrop because it has a larger area. But remember that this is area to volume ratio, not just the area alone. And so what we have to do is look here at what the relationship is between the surface area of a sphere. We'll assume that these droplets are spheres. And it turns out that they're not always spheres. If the raindrops are small enough, they're pretty much perfect spheres. If the raindrops are larger, they will tend to flatten out. They'll never look like a teardrop, though. A teardrop is a misconception because of the way in which rain droplets hit your windshield and gives this kind of an appearance. So you get a little drag here and then it kind of opens up. But raindrops tend to flatten if they're large enough so that they experience some drag in this direction. Okay, but the area of a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. And so the area to volume ratio is going to be 4 pi r squared divided by 4/3 pi r cubed. And so that's just equal to 3/r. So in other words, bigger values of r give a smaller value for the area to volume ratio. So in other words, even though the area is getting bigger in this drop, the area to volume ratio is getting smaller because the volume is increasing even faster than the area is. And so that means that smaller drops then have a bigger area to volume ratio. This is a smaller r value. When you divide by a smaller number, that gives you a bigger number for your quotient. And so that means that these smaller droplets then tend to evaporate quickly. And so it's hard to get from this stage to that stage. Smaller drops and so what you need then is a continuous supply of these water droplets, which you can get if you have a high degree of saturation within the cloud. So this typically will happen in the tropics because there's so much water being evaporated off of the warm oceans. And so that gives you a lot of water vapor to work with. So you just keep force feeding these smaller cloud droplets, and most of them evaporate immediately, but every now and then you get one that kind of catches on, and it starts to build up more and more size. And as it gets bigger, its area to volume ratio drops. And so with a smaller area to volume ratio, then the evaporation rate slows. And so that means that the drop continues to get larger. And so this can happen in a super saturated part of the cloud up here, as you can get a very large drop. But then as it falls down to lower elevation where there is a little less water content, this will break up into smaller drops. That are on the order in size of perhaps 1 millimeter or so. Or in this case, we're talking about 2 millimeters, which is about 2,000 micrometers. So in the tropics then, we start out with smaller droplets that have a huge amount of moisture content and can eventually coalesce into larger droplets. This is not the preferred mechanism, though, at higher latitudes because there's less evaporation. It's colder temperature, less evaporation. That means there's less water available to force feed these smaller droplets and turn them into bigger ones. And so that is why the preferred mechanism at higher latitudes, where the temperature is colder, is to first have ice crystals seeding the supercooled water, and have the supercooled water then forming on the ice crystals to create larger ice crystals, and then at the bottom part of the cloud have the ice crystals melt to become the standard kind of rain that we feel in California. Now, what about hail? Well, the indications are with hail is that we have stronger than normal updrafts. So this means then that we have a cloud which is particularly unstable. That rises very rapidly. And so typically then these kind of cumulonimbus, they may start out with a flat base, but they'll also have a flat top, which we talked about before. This is the anvil-shaped cumulonimbus that is truncated with this vertical development at the tropopods. Which is where we have our temperature inversion produced by the stratosphere. And so you've got these very strong updrafts in here. And so this keeps the ice crystals up in the cloud for maybe as much as 5 minutes. It's thought that the rain has to stay at that very low temperature for up to 5 minutes. and they accumulate into larger ice pellets. In some cases, there will still be some melting on the way back down, but typically the size of these things can range from the size of a pea to golf ball size or bigger. And so here we see some beautiful pictures of different kinds of ice crystals. But then imagine those ice crystals growing more and more until we start getting these big chunks of ice. And so they could start out, say, just the size of a pea, but they could get as big as a golf ball. Okay, and so if they get as big as a golf ball, they've been known to fall and hit you pretty hard. And as a matter of fact, I was up in the Sierras a few years ago, and I felt this sudden drop in the temperature, and my friend said, "Do you think we should take cover?" And I go, "Oh, no, we'll be fine." And then these golf ball sized hail pellets started hitting us, and it really hurt. And if they had been a little bigger, they could have done some damage. And they've been known to break windshields of cars. So it is something to take seriously if you've got these golf ball sized hail pellets coming down on you. Another type of precipitation is what's called sleet. In sleet, basically what we have is got ice crystals form. They fall through the cloud. But then through a layer of warmer air. And they melt. So here is our formation of the ice crystals. The ice crystals fall. Then in this region, this is the warmer air which causes the melting. So they turn into water droplets in this region, and then they drop back through colder air again. So they refreeze into small pellets. So this is the sleet that we can experience under those conditions. You can also get what's called freezing rain. And freezing rain is simply supercooled water that hasn't turned into ice yet. have the temperature here is somewhere between 32 degrees Fahrenheit and minus 40 degrees Fahrenheit. By the way, minus 40 centigrade and minus 40 Fahrenheit are the same. So we could also say this is between 0 degrees centigrade and minus 40 degrees centigrade. And that would be saying the same thing. Okay, and so we have these are just rain droplets until they hit your skin. And when they land, they coalesce almost immediately into ice crystals. Why? Because there are many ice crystals that have already formed if the temperature is below 32 degrees. And so the water then is just waiting for an opportunity to turn into ice. And so typically then it tends to do it on contact. To produce this very unpleasant effect that is known as freezing rain.